Hi everyone, thanks for joining us for today's webinar. My name is Alexi Kazarin, and I'm the Imaris Regional Sales Engineer for the Northeast US. Today I'm going to be showing you how you can use Imaris Stitcher to effectively stitch your tile microscopy acquisitions. So let's get started. First, I want to introduce the concept of stitching as well as the stitcher itself. We'll then go directly into the software where I'll be able to show you how to easily stitch different kinds of data. To start off, stitching is an essential part of many imaging workflows, especially for those of us working with bigger data. We often want to image large samples, some of which can be much larger than a single field of view of our microscope. To do that, we can equip the microscope with a motorized stage and take tiled acquisitions, increasing our effective field of view by taking multiple images around our area or volume of interest. While modern hardware can give excellent results, there are several challenges that can arise in collecting tiled acquisitions, including stage positioning and camera rotations, which need to be corrected for to get a nice seamless image. So this is where stitching comes in. By taking tiled acquisitions with overlap, like this, we can use these overlap regions to computationally stitch our image together from separate tiles. Now, a good place to start would be at least 10% overlap, as I've indicated on this example figure here. To perform stitching, you can use Imaris Stitcher, which is a standalone companion application to Imaris. This application is designed to make it easy for you to stitch tile acquisitions with a fast alignment and interactive preview during the process. The Stitcher can stitch 2D, 3D, and 4D tile data, and is capable of processing big data as well, which we've tested up to 2 terabytes. As an input, Stitcher accepts Imaris.ims files, and its installation comes with the Imaris file converter to help you convert your images before processing. As an output, you'll get one nice big .ims file that can be directly opened in Imaris for further visualization and image analysis. Along the way, Stitcher helps correct for common errors in tiled acquisitions. The first one I want to talk about is camera rotation. Now in this context, the camera represents either an actual camera on your microscope, for example in wide field, light sheet, or confocal spinning disk applications, or it can also be a single scanned acquisition in a normal laser scanning confocal or 2-photon scope. The problem is going to be the same for both cases. And the problem is such, it's camera rotation, that is, the axis of your camera is not perfectly aligned with the axes of your motorized stage. As such, while we would expect a clean acquisition with neat overlap while moving the motorized stage around, we actually end up with a skewed acquisition due to this misalignment. Fortunately, Imaris Stitcher is well equipped to deal with this. The second issue we often see is stage positioning, which is simply due to the mechanical inaccuracy of a motorized stage, which can impact the distance that the stage actually moves when given a command. While we would expect perfect positioning as we move along, the resulting images can have variation in their overall position that deviates from the exact coordinates we've asked the stage to move to, as you can see in the exaggerated example here on the right. So the Imaris Stitcher also corrects for this while stitching your tiled acquisitions. So then, how does it work? Well, to make things short, we first select the resolution level of our stitching during pre-processing. The Stitcher is then going to perform pairwise alignment of overlapping images based on their image content in the overlapping areas, and use this to model the camera rotation for the entire set. So this enables correction for tiles that have little signal or overlap with their neighbors, like this tile in comparison to the bottom right one. After this, the Stitcher then performs global optimization and finds the best position for all the tiles, using the method described by Prybish in the paper below. After some final error checking, the Stitcher then resamples the overlapping areas to create a seamless image. And that's it. So now that we've got a primer on stitching, let's go into the software and take a look at some images. The first thing I want to show you is how to get your data in the Stitcher, and then we can talk a little bit about the interface. On the top left, you can add or clear images currently loaded into the software. As an alternative to the Add Images button, you can also drag and drop your data directly into the Stitcher. Now, as I mentioned before, the Stitcher works directly on .ims Imaris files. If it's not in the .ims format already, a new window with the Imaris file converter will pop up to help take care of that first. Now, to show you how you can easily get data in a stitcher using this approach, I'm going to import and stitch a dataset that consists of 200 TIFF files. So this is a set of 4 image stacks of a mouse brain, and each stack should contain 50 Z slices. The name of each of the slice files contains a stack number here right after the name, sample name mouse brain. And it also contains an underscore with the letter Z and the number that is basically the slice number. So this underscore Z is called a delimiter, and Imaris can track these to help set up data correctly when importing big data sets like this. So the first step will be to drag and drop all of these TIFFs into the stitcher, which will then launch the file converter directly, as we see here. Now on the file converter, you'll see that the input path of your images is already filled in, and by default, the converted.ims files will be saved in the same directory. To make sure that TIFFs making on my dataset have been correctly detected, I'm going to click on the Settings button. First, I'm going to click on the dataset and then the Settings button. And I'm going to go under File Names with Delimiter here. So here we can see that by default, the file converter has detected my Z delimiter correctly for the Z slices. However, because mousebrain isn't a known file splitting delimiter, the number after mousebrain was detected as time points. Since what I want is to get 4 distinct .ims files, each representing a single stack that I'm then going to stitch together, I'm going to change that T to F split here, which indicates to Imaris that this delimiter just represents different files. I'm then going to click on Start All. I'm going to click on OK and Start All to do the conversion. And now in the original directory, I can see the 4 IMS files that I wanted, representing the 4 stacks. And now I can drag and drop these in a stitcher to begin our stitching. Now you can see on the top left that I've loaded 4 images, yet I'm only seeing 1 right now. This is because my TIFFs don't have any positioning metadata from the motor, from the stage, so that we don't know what their positioning is, and so right now they're one on top of each other. If I was to convert image files that do contain the stage position metadata, then they'll be automatically tiled accordingly, and I'll show you an example of that later on. Now in the main view here, I can move my images around with the mouse to place and align them by hand if I want to do that. For example, here. I can also pan around the images with the right click, zoom in and out with my mouse wheel. And if I want to get back to a view that fits all my data, I'm just going to click on the Fit button on the bottom right here. At the same time, we can also see that right now we're in a 3D view, which is a maximum projection from the top of your stack. But like I said, these are stacks of 50 Z slices. So if I want to see my alignment on a slice by slice level, I can just click on Slice View here. And a new bar appears on the left here that lets me go up and down in my slices to compare alignment on that level. So I'm just going to go back to 3D view here. So the first thing I want to do to properly stitch my images is going to be to position them on the grid. To do that, I'll need to know how my acquisition was performed since I don't have that positioning metadata. However, I know that for this data set, we're looking at a 2x2 grid, and that this was taken at a snake by columns and left and up setting. And now we can see some of these overlapping features. You'll notice as a final step here, we've got a % overlap. Now this ideally should be the actual overlap of your image as you required. However, if you don't know it, that's okay. Imaris is going to be able to take that into account and find the proper one. So in that case, I would err on the side of caution. For example, here I can make it a bit bigger. Let's say it's 20%, exaggerating the overlap a little bit, because like I mentioned before, the alignment here is going to be performed on the overlapping regions. So if we feed it more data, better chance that you're going to get better alignment. Okay. Now, as I'm doing this, on the right side, I also just want to mention that we've got our display adjustment. here, which is very similar to the one inside of MARIS itself, where you can change channel colors, turn them on and off, play with their lookup table here, making them brighter or less so. So this is going to be very similar to what Meredith and Anna showed in the last couple of webinars. Okay, so now that I've got my images on the grid, on the bottom left, we'll find our main alignment settings, and by default, the advanced settings aren't visible, so I'm going to click on them here. Now, as a first setting, we have the smooth filter width, which is basically setting up what resolution level we're going to be doing our alignment at. Now, by default, this is the width 4 pixels in your original image. And this is because it helps make the stitching a little bit faster. So a bigger smoothing value will be faster stitching, less noise will be taken into account, but this will reduce the precision of the alignment for smaller features. Now, you should know that this does not affect the final resolution of the stitched image. And even if the alignment is computed at a lower level like this, the overall translations and corrections are going to be applied to the original high resolution data during the final stitching step. So you're still going to get that full resolution of your original image. Now, by default, you'll notice also that the alignments perform on the first channel. So for multi-channel images, which I'll show you an example of later on, you're going to be able to select which one you want to do your alignment based off of. It should probably be the one that is most representative of the features that you want to align. The last alignment setting here is going to be the ability to perform background correction on your data before the alignment. Now, depending on your image features, this may be of benefit to you. However, if you're stitching more noisy data that is closer to background levels, then it may be a good idea to turn this off. So to do the alignment process, I'm going to click on Align All Images. Automatically perform and apply the alignment, as we see here. I can use my mouse wheel by scrolling in and out to have a look and see how the alignment worked, which seems to be pretty good. In this case, it is a simple example, but nonetheless, there are still 50 Z-slices involved. Okay, so once I'm satisfied with my alignment, I can click on Save here to create my final stitched image. So here I'm just going to give it a file name such as stitched. And it will be, as well as being saved in that directory, it will be open in the MARIS if you've already have it installed on the same computer. And here we go. We now have our full final data set from the 4 tiles available in MARIS for doing more analysis or any other additional steps that you want to do. Okay. Now the next thing I'm going to do is I'm going to open a larger tiled acquisition of a Capsella embryo. So I'm going to clear all here. And this data set is quite a bit larger at 26 gigabytes. So I'm going to just navigate here to set 2. And we're going to be able to stitch it as well. You'll see the performance is going to be actually quite good, despite it being much larger than the original data set that I just did. So what I'm going to do, these are already .ims files. I'm going to drag and drop them in. And you'll notice that after the files are loaded, they're automatically placed according to their position from the acquisition data. So they're already on the grid. This is because the position was encoded in the metadata of this image. And this was taken on an Andor Dragonfly spinning disk confocal. Now, on a bigger image like this, it can be sometimes useful to just stitch a smaller area. So in Stitcher, the way to do that is you can shift-click on the images that you want to stitch separately. So here I've got these 4, and I can click on Align Selected Images. So that will perform the alignment process on just a smaller subset here. Now here, what I actually want to do is stitch my entire data set. So I'm going to click on Reset Images to Original Positions to get my tiles back where they were. And then I'm going to play around just a little bit with these settings here. So the first thing is I'm going to switch the alignment, the setting of smooth filter width to 2 microns, just because we can sacrifice some resolution here. You can see it's a huge image. And we don't need that kind of resolution level necessarily, and it'll speed things up. And the other thing I'm going to do is I'm going to pick an alignment channel. So zooming in on the features here, we'll see on the top right that we've got 3 channels, GFP, RFP, and 637. And I'm just going to go look at each one of these in turn to see what features are going to be visible there. And it looks like to me that the 637's got the most features visible across the entire image. So I think I'm going to use that to stitch my data here. So I'm going to select it here, channel 3, and we'll leave the background subtraction on. Then I'm going to align the image by clicking Align All Images. And that's going to be happening here on the bottom right. So you'll notice the alignment process is still quite fast despite the data being quite a bit larger. And I'm going to toggle all the channels in and use my mouse wheel by scrolling in to take a look. That looks pretty good to me. All right. So now what I'm going to do is I'm going to save this tiled acquisition. I'm going to make it into a final stitched file. And as this happens, I just want to mention briefly how the resampling works, because that's what it's doing most on the progress bar here. So as we've now have some overlapping regions, the software needs to be able to put them together into a single seamless image. And so within these regions, we're going to have to do some resampling, which can be done in one of 2 ways, which I'll show you how to change in the preferences in a moment. So the common approach, and the one I use the most, is going to be the weighted mean. That is, the intensity used between 2 neighboring tiles is proportional to the pixel's proximity to each neighboring tile. So this gives results, and good results in most cases. Now, the alternative is sample closest, which is simply the intensity used between the 2 neighboring tiles is exactly the intensity present in the closest neighboring tile. And this can be useful for some images that suffer from optical aberrations, where maybe the weighted mean gives you less visually pleasing result. Okay, so now the resampling is nearly complete. And once that is done, we're going to be able to see our image directly in Amaris itself. Just popping up on my second screen here. And there we go. So I'm just going to reset the lookup table a bit to get it to look like what I want, what I would typically expect. And we've got our final image here. Great. Okay. And this is a moment where I just want to know the distinction here between the Save button, which I've been using so far, and the Save Project buttons on the bottom. So these you can use if you're working on a data set, you're not quite sure of the settings yet, or you haven't had time to make the final stitched image. You can use this to save basically a summary of your current project. And if I clear all here, I'm going to be able to open my project and get back to the exact same status as I was before. So this saves just a little XML file that keeps track of where the tiles are and the settings and everything. It does not actually make a full copy of your image data, so you do save a lot of space by doing that. So keeping track of your progress with save and open projects here. All right, now as a last example, what I'm going to do is stitch a 2D data set that I took myself during my graduate work. So this data set's going to include label-free 2-photon fluorescence as well as second harmonic generation imaging of a rabbit vocal fold cartilage. So as you can imagine, rabbit cartilage can be quite big. So these files were collected on an older Olympus system, and they're OIBs here. Now, as you would normally see with the Maris, we can convert proprietary image formats like OIBs, CZIs, LIFs, and all that. directly into our MARS file format. So all I'm going to need to do here is I'm going to drag and drop these. It'll open my file converter as we've seen before with the TIFFs. But unlike the TIFFs, I don't really need to specify anything. I can just go start all and have them converted right away. We can see it's happening quite fast in the background here. So these images are going to be 36. There's going to be 36 fields of view. I'm going to drag this in now. And as with the TIFFs, though, we don't have any position metadata here. However, I do know how these images were taken, and that's going to be a 4x9 grid done snake by rows with right and up. And that gives me the grid arrangement. I'm then going to just set these colors to be something a little more pleasing than when I was acquiring them, because I was worried a lot about saturation. And like so. And now we've got our data set. So I can zoom in a little bit to have a look at the data. And if I untick show image border, that allows me to have a look at the full data set without the yellow lines. I'm just going to put that back on now. All right. So here I'm just going to adjust the settings a little bit. Now, haven't taken this data set myself. I know that the resolution per pixel here was 250 nanometers or 0.25 microns. So here I'm going to adjust the smooth filter width a little lower than the default because I want to be able to stitch those smaller features here, the cells present within the cartilage. So I'm going to set this to about 350 nanometers or 0.35 microns. And as an alignment channel, I'm going to use my second channel just because it's got more widespread features. So this is the fluorescence channel, whereas the cyan here is going to be second harmonic, which mainly highlights collagen, which is on the sides. So I'm going to use that second channel to give me a better alignment. And then I'm going to click on align, which happens pretty quickly here as well. And now zooming into my overlap regions, I can see it's done a very good job here. I don't see any doubling of features or anything like that. So now I can also save this data set. Just like to name them stitched. Resamples fast because this is a single Z slice on each. And we've got our final data set in the MARS as well. So as you may know, we can analyze 2D data as well. So, and we can stitch it as well, as you've seen today. Okay, so as you can see, stitching tile acquisitions doesn't have to be complicated. Now, the last thing I want to talk about is going to be some advanced preferences, which you can access here on the bottom left. That pops up my other window, of course. So under the preferences, things to pay attention to will be the data cache here, which is just the amount of RAM you want to allocate to the program. So you want to set this to be maybe 80% of the RAM on your computer. This should be the texture cache size of your graphics card or your GPU in megabytes, not in gigabytes. So just pay attention, maybe to note here. And the number of parallel jobs, which is really can be the number of your CPU cores, automatically usually detected to be the same as number of CPU cores. Okay, and here's where we've got the resampling method I talked about. So you can choose whether you want a weighted mean or sample closest in those overlap regions. I usually stick to weighted mean, and this is where we're pointing it to our MRS application here. And that's all there is to it. So as you can see with a MARS stitcher, you can stitch both small and large data sets, 2D and 3D, and you can get them ready for your next analysis step, whether that's going to be visualization or animation or some deeper segmentation in the MARS itself. So I hope I've given you kind of a good overview, and let me know if you have any questions.
Hi, everybody. This is Meredith. Sorry that the recording kind of cut off a little bit at the end. We're gonna now uh, answer some questions. So I'm gonna read them off to Alexei, and let me just make sure Alexei's there before I read it off. Are you here?
I'm here. Yeah.
Sweet. Okay. So a few people asked if it's possible to stitch bright field images.
Great. Thanks for the question. That's something that comes up quite often. And yes, the Stitcher can do bright field images as well.
Okay, and then can it take care of the dimmer region at the junction of the images that need to be stitched, which is generally found after stitching?
Yeah. So the dimmer region at the junction of images like that is often caused by uneven illumination. So that's often more of an acquisition side, an optics side of things. So it's not something that we correct for at this time, but this is definitely a very interesting feature request for us to
Mhm.
consider.
Yep. And then I think you covered this, but just to make sure everybody's clear with the answer, does the Stitcher read stage coordinates from image metadata?
Yes, so the Stitcher does read it if it's available, and that's why we recommend converting from your native image format from your microscope that does contain metadata if it's available instead of using an intermediate like a TIFF, which is probably going to lose these coordinates.
Yep, exactly. And then the last question, can stacks with differing z heights and or differing upper or lower limits be stitched together?
Yeah, so that is also something a Stitcher can do. Just want to make sure you do still have some overlap in content between the images.
Yep. Great. Well, thank you so much, Alexei, for taking us through Amara Stitcher. It was a really nice overview. And if anyone has any questions, I'm sure there's some extra questions being asked right now that I just can't see. What we'll do if your question hasn't been answered already is that we'll get those out to our sales and support team and they'll reach out to you. Within a few days to get you those answers. And then if you have additional questions, feel free to reach out to your local support or sales rep as well. And thank you so much, everybody, for joining. And feel free to tune in to the next webinars that we're having in the following weeks. So yeah, take care. Thanks again.
Thanks, everyone. Take care.